Alright, this first video in our study of electricity is largely just going to be a review of some terminology and some ideas. So there's probably going to be very little new information, but it doesn't hurt to go over it again. So first of all, we have the idea of the electric charge. And electric charge is an intrinsic property of protons and electrons. And basically what that means is we don't really know what the source is. It's just what it is. Kind of like matter has mass, I mean, we don't know where that comes from. So it's the same thing with the electric charge. As you already know, there are two types of charges. We have positive, which is the proton. The proton carries a positive charge. And then electrons is what gives us a negative charge. That's the intrinsic property of the electron. Now, when two charges are brought near each other, those charges are going to experience a force. So if we have charge 1 and charge 2, here's a positive charge and here's a positive charge, then what we get is the positive charge on the right feels a force due to charge 1, and on the left side we have the force on charge 1 due to charge 2. If we have two negative charges, then we see the same thing happening. We have the force of charge 1 on charge 2, and we have the force of charge 2 on charge 1. And then finally, if we have two opposite charges, then we know that they will attract. So we have the force of 1 on 2, and then the force of 2 on 1. Now, up to this point in time, all of our forces have been contact forces with the exception of gravity. So this is going to be our second non-contact force. In mechanics, gravity was the other one. So when we're drawing our FBDs, we know that only those things which are touching the object that we're focusing on are going to exert a force, now with two exceptions. One if we include gravity, and the other is now the electric force. In most problems that we do in electricity, we actually ignore gravity because gravity is so small compared to the electric force. And what I mean by that is this. If we look at the force of gravity fundamentally, we know that it's proportional to the constant g, which is 6.67 times 10 to the minus 11. When we look at the electric force, we know that it's going to be proportional to the constant k, which is 8.99 times 10 to the 9th. And so you can see that there's 20 orders of magnitude difference, and that's just going to be huge. The other way we know that gravity is going to be very small compared to the electric force is because of, it takes something the size of a planet to generate a relatively small force on, say a person or a baseball or an apple. You can easily pick an apple up off of the ground. Well, when it comes to electric forces, it doesn't take a whole lot of charge to generate a very large force, and that's even on a small object. And we'll take a look at that more later. The idea is, though, that the gravitational force is very, very small, and as a general rule, it is going to be ignored. There are four basic types of materials. The first one is going to be a conductor, and Conductors are those materials where the charges move freely between the atoms. So examples of conductors would be metals and solutions, ionic solutions. The second type of material is going to be an insulator. And an insulator is just the opposite of a conductor, so the charges are not free to move. Our third type of material is a semiconductor. And semiconductors are actually central to our modern technological society with all of our electronics. And semiconductors are used to create electronic switches that are not mechanical in nature. And so we're talking about diodes and transistors, and those are central to everything that we do in electricity these days, in modern electronics. Anyways, a semiconductor is one where there are major conductivity changes which are determined by environmental factors, and the big one there is going to be temperature. As the temperature increases, the resistance of the conducting material, the semiconductor, decreases. And that's the exact opposite with metals. With metals, as the temperature goes up, the resistance also goes up and it becomes less electrically conductive. The fourth type of material is the superconductor. And the superconductor is one in which there is no electrical resistance, but that only occurs at very, very low temperatures. Okay, the ultimate goal of scientists who are researching superconductors would be to have a room temperature superconductor. And that's important when it comes to our global economy that we have today. The energy consumption of the world at large has increased many times over as third world countries are developing. The developed countries continue to become more electronic with everything that they do, and electricity is central to everything. And basically what happens is they're generating electricity at the power plant, but 40%, approximately 40% of the electricity that's produced is lost as heat inside the power lines, transmitting it from the power station to your home or wherever you're at. And so room temperature superconductors, of course, would really diminish the amount of energy which is lost. Additionally, we always hear about these terms charging and discharging. So to charge basically means that you're going to create an excess or deficiency of electrons. And the reason why it's electrons is because protons are bound to the nucleus of the atom, and if you remove a proton from the nucleus, you no longer have whatever type of atom you're looking at. You have a nuclear reaction, which is resulting in a new element being created. So if something is negatively charged, then that means you have an excess of electrons. And if it's positively charged, you have a deficiency of electrons. Most materials, most objects in the universe are neutrally charged. And basically all that means is there's approximately the same number of protons and the same number of electrons in that material. Now it's never exactly the same. Just walking through the hallway, you might brush up against somebody who actually has a little bit of static built up on them, or maybe the wind is blowing and you're outside, and so, but you're always very, very close to being neutrally charged. Now, if charging is creating an excess or deficiency of electrons, discharging is the idea that you're neutralizing that, or you are going to decrease the surplus or deficiency. Okay, now let's take a look at the ways that we can charge. And there are three ways. The first way of charging is by friction. And typically this is going to be insulating materials that we're charging up. And when you're charging by friction, you are literally pulling electrons off of one object and they're sticking to the other object. Charge is always going to be conserved, so whatever object loses electrons, the other object is going to gain electrons. And we'll do some activities in class relating to this type of charging. The second type of charging is charging by conduction. And conduction occurs between two conducting materials, and it is by contact. When two objects are charged through conduction, they simply share the electrons. And what I mean by that is this. If you have a conducting sphere here that has 5 coulombs of charge, and you have a neutral sphere over here, then when you bring these two spheres into contact, you're going to end up with, as long as they're the same size, you're going to end up with 2.5 coulombs on the left and 2.5 coulombs on the right. Finally, the third type of charging is done by induction. And inductive processes are non-contact. Nothing needs to be touching in order for this to occur in terms of the charging itself. Now, as part of the process, there's going to be some contact, but not of the two objects in question. All right, so it is going to require some type of ground, because what you're going to be doing is pushing electrons around by way of electric fields. So whenever you get two charges in close proximity to each other, they feel a significant force, and so they try to get as far away as they can. They repel. So you need some type of ground, or what we could call a source or a sink for electrons. Okay, and a ground, we're going to define this here in a second. A ground is both a source and a sink, depending on whether the electrons are being added to or taken from the ground. But the ground is special in that there is no significant change in its overall charge. And whenever I'm referring to just the source or the sink, there may be a significant change. And so that's why it's all these slashes, a ground / source / sink. So a ground is a conductor which is sufficiently large such that the net change in the charge is 0. And I want to demonstrate this, I loosely say demonstrate this, using a capacitor, which is just a device which can store charge, and then use a penny as a ground or a cookie sheet as a ground. And if we make some comparison here, an average capacitor, it may store charge on an area which is, we'll say, 100 square centimeters. Okay, because a capacitor, if you recall from last year, a capacitor is basically two pieces of foil which is rolled up like a jelly roll. Okay, And so if you were to unroll that jelly roll, you'd see that the foil has an area of approximately 100 square centimeters in this particular example. Now, if I wanted to discharge that capacitor, then I'm trying to take all the charges which are on this foil and put them somewhere else. So if I were to try to discharge to a penny, then there would be approximately 3 square centimeters. There's no way that that penny can absorb all the charge off of this capacitor. It just doesn't have the room for it. And so when you discharge the capacitor, you're going to find that there's still a lot of charge left on that capacitor. On the other hand, even a small cookie sheet has 1,000 square centimeters, if not more. And so if you discharge this capacitor into the cookie sheet, what you're going to find is that this capacitor probably has less than 1/9 or 1/10 of whatever the original charge was. And at that point, you may consider that capacitor to be discharged. So that's what we mean whenever we say that the conductor is sufficiently large such that there's not a whole lot of change in its overall charge. And of course, if you actually use the earth or literally the ground to discharge the capacitor, then it would take the capacitor to virtually zero net charge. All right, so when we charge by induction, the process goes something like this. So we've got a charged sphere, a neutral sphere, and it is connected to an insulating stand. And we bring, let's do it like this. And distributed throughout the sphere are protons and electrons. Okay, this is considered to be neutral. All right, now what happens is this. Here's my sphere, my conductor, there's my insulating stand, and I bring near it a negatively charged rod. Now what happens is the electrons in the rod produce a force, create a force on the electrons of the globe. And so the electrons in the globe, being negatively charged, are going to be repelled to the back side, leaving a positive charge on the front side. Now at this point, you have not actually created a charge because this globe as a whole is still neutral. So it's technically not charged yet. It is what we call polarized. And to be polarized means that you force the charges into separation. So what you have are regions of positive and negative charge, but as a whole, this thing is going to be neutral. Now, here's the trick to the process. There's our globe. And what we're going to do is we're going to bring in a ground. And basically what we're doing is giving those electrons somewhere to go. So the electrons, they go through that ground wire. All the while, we have not moved this negatively charged rod, which means, being that the protons are bound to the atoms, they're in the nucleus, we have a positively charged globe. Now, at this point, the globe is charged, but if you were to move this negatively charged rod away from the globe, those electrons would go back up the wire into the globe. So, in order to actually create a permanent net charge, you have to remove the ground wire first, and you need to have this type of situation here. You've removed that ground wire. And now you can remove the charged rod. And when that charged rod is removed, this globe is going to stay positively charged. Induction produces opposite charges. So what I mean by that is this. This rod, this charged rod, it was negative, but what I was charging became positive. And that's what I mean by that. Now, this was an example where I used a ground. You could do the exact same thing if you wanted to create a positively and negatively charged sphere. So here's my negatively charged rod, and I have two spheres which are in contact with each other. And when I do that, I push the electrons onto the sphere on the right, leaving a net positive charge on the left. And before removing this rod from close proximity to those two spheres, you separate the spheres so that each one maintains its overall polarity. So the one on the left is positive and the one on the right is negative. There's one or two more things I want to talk about very quickly. And one of them is that charge is quantized. And basically what that means is it comes in a discrete unit, a bundle, a packet, something that cannot be made any smaller. And the example I like to use for that is eggs at the grocery store. You can buy a dozen of eggs, that's no problem. And you can buy a half a dozen of eggs at most stores, and that's not a problem either. Now, if you only need one egg, you can probably argue with the store manager, and he may sell you one egg, but it's going to cost you as much as a half dozen. But if you argue enough, you'll be like, no, I don't want the other 5 eggs, I just want the one egg. It's quite possible that he hands you an egg out of the carton, throws the rest of the eggs away, and you walk away with your one egg. But under no circumstance, no matter how much you argue, no matter how much you pay, can the store manager sell you half an egg. And that's what it means to be quantized. It means you can't divide whatever that thing is any more than it's already divided. An electric charge is the same thing. So mathematically, we write this quantization as Q is the variable that we use to represent charge, is equal to capital N, which is an integer, times E. So the Q is basically what you measure macroscopically. All right, and that can still be a very, very small number. N is an integer. And this letter E is not electron. It is the fundamental charge, and the fundamental charge E is equal to 1.6 times 10 to the minus 19 coulombs. Now, an electron charge is going to be E with that little minus sign. That's 1.6 times 10 minus 1.6 times 10 to the minus 19 coulombs. So be careful that you make that distinction. Anytime you see that letter E, we're not talking about an electron. However, one electron does carry a charge in magnitude equal to our fundamental charge. So, just be careful of that. It's important to note that in metals, because in physics we really deal with a lot of metals as our conducting material, and so that in metals, electrons are the charge carriers. However, electrons are not the only thing that can carry our charge, and so if you have a solution, ions can also be charge carriers.